I'm Evan Walters,
And I'm Nathan Schultz.
and this is Foundations and Footings.
So, what is a foundation, you might ask?
A foundation, that's the club on Northgate, right?
No, Evan, we're engineers. We don't have time for that.
Oh, that's right, we're engineers, I'm sorry. Foundation is the lowest point on a structure that carries all of the load. In the olden days, it could have been something such as a rock at the corner of your Lincoln log cabin, or a wooden piling at the corner of your hut.
If this concept is even taken to the extreme, you can see here that the hammock with the trees might also be considered a foundation.
But I don't typically sleep in a hammock every day. So I'm a big city guy, you know? And modern foundations are typically made out of reinforced concrete. And here, in each of these little foundations is called a footing. That's part of the foundation. Within some structures, in places such as Mexico City, you can have the foundation extend all the way down to the bedrock of the structure, and this helps prevent consolidation's effects in the long run.
So now we're basically going to talk about some of the different types of foundations and footing types that we can see out in the field. Here you just see along the top just some very simple ones. You might see something like a simple wall footing, which basically carries the bearing wall load. Over here you might see a simple column footing, which is either going to be a simple square or rectangular to carry that single column load. As Evan was describing earlier, sometimes you can have pile footings where those pile casts will go all the way down to the bedrock to prevent the consolidation of the soil. Even sometimes you might have specialized cases where you have the mat footings over here, which is basically a large footing that's going to cover a larger area because the bearing capacity of the soil isn't as highly needed. So,
have you ever wondered how an arrowhead is made?
Yes, I have.
An arrow, whenever an Indian would take the two rocks and pound them together, the energy from the impact splays out through the rock in a conical fashion. If the Indian hit the arrowheads in the correct angle, then a piece would break off and they had a very sharp edge and could reshape that into an arrowhead. This conical splaying out of energy is similar to what happens under a footing, and as one can see here, under the footing, the energy goes down in a conical fashion, pushing the soil under it, below it, downwards, and then due to Newton's third law, the soil around it is pushed outwards and upwards because the soil pushing downwards. This can also be seen in this diagram. It's being pushed down, out, and up. As you get farther from a footing, typically the soil that is farther from a footing is impacted less by the load on the footing than the soil directly beneath it. This we have learned in our geotechnical engineering studies in Civil 365.
Now that we've talked about what happens under the footing, we're going to talk a little bit more about what happens inside the footing itself. Now, some of the things that are happening on the footing is you have different types of loads and reactions, as you can see over here, that are coming down on that footing. In this diagram you can see that the column is pushing downwards onto that entire footing. And there's going to be some things that are going to happen there. Is you're going to have a peak shear force right at the base of the column there. And then at the edges, actually, you're going to have a peak moment where that bending moment, the bending of the footing is caused highest over here. As you can kind of see in the diagram, it's got that little bending shape. And so because of that, we're going to have to design some reinforcement for that. Typically, for the moment, we're going to design some... As you can see in this diagram here, this is kind of a diagram of a very detailed picture of what's happening inside that footing. So like I was saying, for the moment, typically you're going to have some reinforcement along the bottom there going in both directions to resist that bending moment that wants to occur. For the shear, typically the design is the thickness of the concrete. That concrete is just designed to resist that shearing force, which is just the column and the footing rubbing against each other. Now for the dowel rods, those typically are used as just to increase the bearing capacity of the concrete, so that way to resist the bearing load of the column on the footing itself.
After a footing has been designed, it is necessary to calculate development lengths with regards to detailing of these footings. In this diagram, one can see how the loading transfers from the concrete to the steel at that concrete and steel interface. Here, the length of the triangle, or the height of the triangle, is the length of the development length. And as the triangle gets smaller, one can see the load transferring from the concrete to the steel. Sometimes it is necessary to further reinforce that concrete, and these dowels are inserted as extra reinforcement within a footing or within a footing, and that unlocks this third small triangle here on the right, which aids in in transferring the load along the development length.
Now that we've talked a little bit about what happens, we're going to practice this with a problem statement. So we have been given the task of designing a square spread footing for the following conditions: that the service dead load is of 350 kips, the service live load of 275 kips, with a soil density of 130 pounds per cubic foot. Further, we have an allowable soil pressure of 4,500 pounds per square foot.
The engineer has designated that the column be 18 inches by 18 inches. Within a footing, typically you can use lower strength concrete, so the compressive strength of this concrete in this example is 3,500 psi. Grade 60 steel is used, that is standard across the board in the industry, and the bottom of the footing is placed 5 feet below floor level. With regards to evaluating the problem, there are 7 easy steps to evaluating it. First, one must determine the factored loadings, as we have always done in class. Second, one must determine the footing size and the soil pressure, and determine the thickness for two-way and one-way shear as a check.
Further, as we talked about earlier, we're going to design that flexural reinforcement to resist that bending moment that wants to occur in the footing. After designing that reinforcement, we're going to check the development length of those reinforcement bars to make sure that they meet development length requirements of the code. Lastly, the designing of the column footing joint will occur where basically the dowel rods will be designed to increase that bearing capacity strength.
With regards to first determining the factored loadings, this is just like how we have done currently throughout our entire study in Civil 444. 1.6 times the dead load, or 1.2 times the dead load plus 1.6 times the live load. Actually, I'm sorry, I made a mistake. It was 1.4 times the dead load for the first one. Then, after you've determined the footing loads, it is necessary to determine the footing size, and the soil pressure. These equations can be used in order to do that. Typically, but the main concept behind this is that you have a soil that will fail under a certain pressure. You put a footing on top of it, and then you must put an area of a footing on top of that soil. What you're trying to do is you're trying to support the footing with enough of that soil so the soil will not fail. So you would take the footing and you design it to be large enough to spread out that load from the column and the footing into the soil. Next, after the footing size has been determined, it is necessary to determine the thickness for two-way shear. Two-way shear is the concept of when the footing has most of its shear load directly at where the column and footing interface is. Now, we're checking for two-way shear so that it doesn't punch directly through the footing and just go into the ground. So within this, it's necessary first to calculate a D average value and a ultimate shear load. After calculating that, it's necessary to calculate a VC value and check that your phi times VC value, your factored VC value, is greater than your shear ultimate value. After that, it's necessary to check for one-way shear, and one-way shear is the concept described in beams earlier, is that it can shear due to the direct bending of the beam going up and down. This is similar to how we have done in class, and etc., etc.
Now, as we design for the flexural reinforcement to resist that moment, it's going to be similar to what we've done many times in this class as we've designed flexural reinforcement for our beams. Typically, you're going to find the ultimate or the peak bending moment that's going to occur along your footing, and then you're going to design and select the amount of reinforcement to resist that bending moment. After selecting that reinforcement, typically you'll find that capacity strength, the factored capacity strength, to check that it's greater than that ultimate moment, because that's just a basic design requirement. As far as development length for those rebar, we typically refer to the ACI code to check the different types of development length requirements specified by the code itself. As far as for designing the column or footing joint, typically you'll find the bearing load caused by that column down onto the footing, and you're going to design the area or the dowel bars to increase that bearing strength to resist that bearing load. Typically the dowel rods are selected in 4 rebars for different sizes, 1 for each corner of the footing. That's just typical design for column footings.
Now, it's your turn. Now, throughout this presentation, you should have acquired the skills in order to do this example problem. Within this example problem, it starts off with a design of a square footing, just like the example we already did. The soil density is 150 pounds per square foot. The allowable soil pressure is 3,000 psf. The dead load and live load are both 280 kips. The engineer has designated that there be 22 by 22 inches square column, and a little hipster 65 grade steel, and also a higher strength concrete of 5,000 psi. Lastly, the footing will be 3 feet below floor level.
So you see here we just have some of our references that we used, just some online sites, and of course the reinforced concrete book for this designated for this class.
Thank you, Professor Barroso. That's all.